Today we're going to look at a really interesting problem related to the divergence theorem. So before we get started on that, let's recall really quickly what the divergence theorem says. So let's say that S is a piecewise smooth, outwardly oriented surface that's bounding a solid region E, which is in R3, and F has continuous partials on an open region containing E, and it's important that it's on an open region containing E. Then the surface integral over the vector field F is equal to the triple integral over E of the divergence of F. Now the intuition behind this is over here you have a triple integral, and inside of that triple integral a fancy derivative, that fancy derivative being the divergence. But that derivative cancels one of the integrals, and that gives you this double integral type object, which is in fact a surface integral. Okay, so what we're going to look at is this vector field F, which is given by x over r cubed, y over r cubed, and z over r cubed, where r is this distance from the origin, so that is the square root of x squared plus y squared plus z squared. So notice this has a discontinuity at the origin, which means its partials are not continuous at the origin. So that's actually going to motivate how we tackle this problem. Next, we want to let S be any closed connected smooth surface, so any one at all. And then our goal is to find this surface integral over S of f dot ds. So this is going to be split into three cases. So maybe case number one would be the origin is on the surface S. So let's maybe kind of sketch up what that looks like. So let's say that's our 3 space. That means our surface S, which might look something like that, it actually contains the origin itself. And so I'm not actually going to work through all of the details in this case, but what you can find out pretty easily is that the integral does not converge. And you can do that by setting up a limit. So our second case will be, what if the origin is kind of away from S and away from E? So what I mean by that is the origin is outside of S and the origin is outside of the region that it is contained in E. That it is containing E. So maybe a little picture of this would be something like, notice the origin's right here, and then we could put our surface would be like a little blob out here that is away from the origin. So that would be our surface, and then the solid that it's being bounded by could be this shading that I'm doing in pink. Okay, good. So the important thing here is that the divergence theorem applies. So the divergence theorem will apply in this case, which means we can take the surface integral over S of the vector field F and say that that is going to be the triple integral over E of the divergence of F dv. Great. But what that means is that we're going to need parts of that. We're going to need the partial with respect to x of this, the partial with respect to y of this, and the partial with respect to z of that term. So let's look at that. So this is going to be the triple integral over E of the partial with respect to x of x over r cubed plus the partial with respect to y of y over r cubed plus the partial with respect to z of z over r cubed. Great, dv. Okay, so let's go ahead and calculate this derivative right here. So I think we'll have enough space to put it right here, and then we'll apply symmetry to find this derivative and this derivative. They're going to be pretty similar, just with x switched out for y and z. So we need the partial with respect to x of x over r cubed, but notice that's going to be the partial with respect to x of x times r cubed minus x times the partial with respect to x of r cubed. And that is all over r to the 6th. Okay, good. So now let's do the derivative of each of these parts. So notice this is going to give us r cubed minus x. So now let's see what the partial with respect to x of r cubed is. So that's going to give us 3r squared and then by the chain rule, we need to take the derivative of r with respect to x. I'll leave all the details of that to you, but that's like a calculus 1 type problem. That's actually going to give us x over r, so I can put an x over r here, and then all of that is still over r to the 6th. So now I'll leave it to you guys to simplify that rational expression. It's not too hard, and what you'll end up with is r squared minus 3x squared over r to the 6th. So just to reiterate, the derivative with respect to x of x over r cubed is this quantity right here. R squared minus 3x squared over r to the 5th it should be. And then similar formulas hold for the y portion and the z portion, just with x swapped out for y and x swapped out for z. So that means this thing is going to transform into the triple integral over e of r squared minus 3x squared over r to the 5th plus r squared minus 3y squared over r to the 5th plus r squared minus 3z squared over r to the 5th. And then we have dv. Okay, fantastic. So let's see what we get here. So this is going to be the triple integral over e, and then I can factor a 1 out over r to the 5th out. And then I'll be left with 1, 2, 3 r squareds. So I have 3 r squareds. And then I'll have minus 3 times the quantity x squared plus y squared plus z squared. And then all of that is being integrated dv. Okay, fantastic. But then, by our formula for r, it's pretty easy to see that x squared plus y squared plus z squared is actually equal to r squared. So we have 3r squared minus 3r squared. In other words, we're integrating 0, and so that's going to give us a value of 0. Okay, so we've covered two cases. One is if S is on the boundary of our solid region E. In other words, it's on that surface. And another one if the surface and the solid region is away from the origin. And in one of them, we get that the integral does not converge. And in another one, we get that the integral is 0. So that leaves us with one more case, and that is if S envelops the origin. So let's get to that. Okay, for our last case, it's the case when the surface S envelops the origin, meaning that the solid region E contains the origin, but it's not on the boundary surface. So let's look at a sketch representing that situation. So we want our surface to envelop the origin, so that means we have this kind of picture. We have this kind of blobby surface that is around the origin. Let's maybe go ahead and draw it like that so we can tell that it's a surface. So notice the surface is not containing the origin, but the solid region being bound by the surface does contain the origin. Okay, good. So since the surface doesn't contain the origin, but the solid region does contain the origin, what that means is we can find a sphere of radius A that is completely contained within this surface. So let's draw that. So let's maybe put a sphere right here. So maybe we'll draw it like that. And that's going to be a sphere of radius A. Maybe we'll do the interior of that sphere in orange. And so how are we going to do that? So let's let A, which is a positive real number, be such that the sphere of radius A is a subset of E. Great. And let BA be the interior of this sphere. So if you know something about like topology or something, you know I'm really not being very careful with my words here. But the idea here is that BA is this orange part, whereas SA is really just the crust of this sphere. Okay, fantastic. But now what we want to notice is that the region given by E minus BA does not contain the origin. And in fact, case number 2 applies to that, which tells us that we have 0 equals the triple integral over this region, E minus BA, of the divergence of F dV So now we'll apply the divergence theorem to this object, and we're allowed to do that because it does not contain the origin. So that's going to give us the surface integral over the boundary of this. So I'll write that in the following way. So del E minus BA, good, of the surface integral f dot ds. Okay, good. So what do we have for the boundary of E minus BA? Well, that is going to be this outer surface S, and then this inner surface, which is blue. So maybe let's notice that. So let's notice that the boundary of E minus BA is going to be equal to this yellow surface, so I'll just put a yellow box in there, and then plus this blue surface. But nothing in between. The stuff in between is E minus BA. Okay, great. So, but now what we can do is notice that we can split this up into pieces. So this is going to be the surface integral over S. That's the yellow bit. So let's maybe underline that in yellow, of f dot ds. Great. And then plus the surface integral over SA. Notice SA is going to be the surface of this ball of radius A, and then this is f dot ds. And now here we need to be careful with our orientation, because the orientation on S is outward. Great, so it's outside of the surface, but that makes the orientation on this SA, remember it needs to be coming out of the solid region, but that means it needs to be coming in. Okay, good. But now, what we'd really like to do is flip that to an outward orientation. So we can flip that to an outward orientation and turn this into a minus sign. But now this equation allows us to solve for our goal surface integral in terms of maybe a surface integral that's easy to calculate. So we have this surface integral over S of our vector field S is equal, of our vector field F is equal to the surface integral over this sphere of radius A of our vector field S. So that means that's all we need to calculate. So I'll go ahead and clean up the board and we'll calculate that. On the last board, we argued that our goal surface integral is actually equal to the surface integral over SA, where A was some sort of radius for a sphere so that it's completely contained within S. So let's go ahead and calculate this just the old-fashioned way by calculating the surface integral. So that means we need to parameterize this surface. So usually when we parameterize spheres, we are motivated by spherical coordinates. So let's just recall spherical coordinates real quick. So that's going to be rho cosine theta sine phi for the x value. Y will be rho sine theta sine phi. And then finally z is equal to rho cosine phi. But that parameterizes all of R3. We only want to be on a sphere of radius A, which means what we'll do is we'll set rho equal to A, and that will give us our sphere of radius A. So now we can take these and make a vector valued function that will parameterize our surface. We'll call it S. So we'll say S theta phi. So in the x component, it will be A cos theta sine phi. In the y component, it will be A sine theta sine phi. And finally, in the z component, it will be A cosine phi. Now next, recall, in order to calculate this surface integral, we need to calculate the normal vector. And we've done this before on the channel where the surface is a sphere, and we recognize that we have to take the cross product in a certain order in order to give us an outward orientation. And that order was like this. So we have S phi cross S theta. So that's going to be the normal vector for this parameterization. Great. So we'll go ahead and calculate that. We'll use the matrix form of the cross product. So I need my I hat, j hat, and k hat vectors in the first row. And now I need my derivative with respect to phi here. So that's going to give me A cos theta cos phi, and then A sine theta cos phi, and then finally minus A sine phi. Good. And then I need my derivative with respect to theta in the bottom row. So that's going to give me minus A sine theta sine phi. and then I'll have a cos theta sine phi, and then finally I'll have 0. So now let's go ahead and do that cross product. So in the first component, which is what we get from crossing this and this out, notice we get a squared cos theta sine squared phi. So a squared cosine theta sine squared phi. So that's our first component. Now let's go ahead and look at our second component, which is what we get from crossing this j out. And in that case, we're going to get a squared sine theta sine squared phi. So a squared sine theta sine squared phi. Okay, and then let's look at what's happening in the third component. So notice here we'll get a squared cosine squared phi sine phi, and then we'll have a squared sine squared cosine squared sine phi. But then we've got a cosine squared plus a sine squared in theta variables that adds to 1. So this is going to give us a cosine phi sine phi. So I'll let you guys check that carefully, but this is towards the end of a multivariable calculus class, so you've probably taken tons and tons and tons of cross products. Okay, now the next thing that I want to notice is that I missed an a squared here. Okay, now let's factor out a common term from each of these just to simplify a bit. So we can take an a squared sine phi out of the whole thing. And then in the first component, we're going to be left with cosine theta sine phi. In the second component, sine theta sine phi. And then in the third component, we've got a cosine phi. Now that may not be computationally very helpful, but it does point out that this is an outward pointing normal vector. So notice this is a scalar multiple of our original parameterization. In fact, if we bring this a on the inside, we see that it is a scalar multiple of our original parameterization pretty easily. Our original parameterization takes us from the origin to the sphere, but now this vector is pointing in the same direction, so that means it's normal to the sphere pointing outwards. So that's good to know. Okay, so now the next thing that we want to do is use this in order to calculate this surface integral. So I'll go ahead and clean up the board and then we'll get to that. So in the previous board we got set up with our cross product, which acts as our normal vector for our surface integral. And let's just recall the surface integral over SA of f dot ds will be the double integral over D, where that's the region that parametrizes the sphere. We'll get to that in just a second, of the vector field evaluated on the surface. So we'll do that kind of as we go, and then dotted into this normal vector, which was s phi cross s theta, which I've written up there just as a reminder. Okay, so now let's get to that. So we can change that double integral over D into an iterated integral. We have 0 to 2 pi for the theta region, and then 0 to pi for the phi region, and that's because we want to find an integral over the whole sphere, and that's what it takes to give us the whole sphere. Great, and now we need our vector field f evaluated here, but let's notice our vector field f is x over r cubed, y over r cubed, z over r cubed, and r is equal to x squared plus y squared plus z squared, but luckily that's going to make r equal to a. And we know that because we're on the surface of the sphere, and that sphere is of radius a. Great, so that means we're going to have x, but recall x by our parameterization is a cosine theta sine phi over a cubed, and then here we have a sine theta sine phi over a cubed, and then here we have a cosine phi over a cubed. And then here I just want to point out that this is the x component right here, and then this is r. This is y, and this is r cubed. I should have said r cubed right here. And then this is z, and this is r cubed, where I'm just using my parameterization for the sphere. Great. And now the next thing that I need to do is dot this into that guy up there. So we're going to dot that into the vector, which has a scalar multiple of a squared sine phi on the outside, and then we have cosine theta sine phi, sine theta sine phi, and then cosine phi. And then, like I said before, we're doing d phi and then d theta. So the first thing that I want to notice is I've got an a over a cubed, which gives me a squared in the denominator, and then I have an a squared here. So that means all of these are going to cancel down to a squared in the denominator, and then when we do the dot product, they're going to cancel this a squared. So now let's go at it. So this is going to be the integral from 0 to 2 pi, the integral from 0 to pi of sine phi, and then we need to do this dot product. So let's color code this. We need to hit this first component with this first component. So that's going to give us cosine squared theta sine squared phi plus, now we need to hit this second component with this second component. So that's going to be sine squared theta and then sine squared phi. Great. And then we hit this last component with this last component. So that's going to be plus cosine squared phi. And now we're doing d phi d theta. Okay, so there's a bunch of simplification that can happen here. So notice we can factor a sine squared phi out of this, and that leaves us with sine squared phi times cosine squared theta plus sine squared theta. But notice cosine squared theta plus sine squared theta is 1, and that leaves us with sine squared phi plus cosine squared phi, so those are also going to add to 1. So that makes everything in these parentheses here just equal to 1. And so that gives us the integral of only sine phi. But now we can use the fact that this is a trivial function of theta times phi, so we can split this up into two parts, a theta integral and a phi integral. So this is going to be the integral from 0 to 2 pi d theta times the integral from 0 to pi of sine phi d phi. So that's going to be 2 pi. Take the antiderivative of sine, we get minus cosine phi, evaluated from 0 to pi. Plug in pi, you're going to get -1, but then we've got this minus sign here. Okay, so now the next thing I'm going to do is I'm going to scrub this minus sign out into a plus, and I'm going to change my order of evaluation. Cosine of 0 is 1 minus cosine of pi, which is -1. So we got 1 minus -1, that gives us 2. So the final answer is 4 pi. Okay, and that finishes this video.